Okay, now we consider or introduce a new concept called category. So the category is a way to categorize the number of elements in the metric space. There are only two types of categories, so we call them the first category and the second category. So the definition is given as follows. So let X D be a metric space. Then let's say look at just a subset, but you can also consider the entire set. We say the set E is said to be of first category. If we can write E as a countable union of nowhere dense sets. Okay, recall that nowhere dense set is the set whose closure doesn't have any interior point. Okay, if a set is not of the first category, then we call it is of the second category. Okay, so what this means, you can imagine that if E is, we know that if EK is nowhere dense, then that means the closure doesn't have any interior point, and that means that just the set is kind of scattered around. So if it's just a countable union of such set, we think that there are not many elements in E. Okay, so that's why another way to describe a set of first category is that the set is meager. Okay, first category. Okay, or if it's second category, we'll call this fat. Okay, how this is going to help us? So let's look at an example. We say the Q is of the first category. And as you can imagine, this is true because Q can be written as just a countable union of the rational numbers. So let's say that each set is a singleton that contains only one element. And this is, let's say this is set EK. Okay, it only contains the rational number RK. And we know there are only countably many rational numbers. That's why the Q is a countable union of this singleton set. Okay? And as you can see here, this Q must be of first category according to the definition. And from this, you can also see that for any set that is a countable set, you can prove that it's of first category, right? Because if it's a countable set, then you just need to take the union of the elements, individual elements of the set, and then same reason, the E must be of first category. Okay. But what we're going to show here is that the barrier shows that a complete metric space must be of the second category. That means there are many elements in the complete metric space. And from there, we are going to get some interesting results. But first, let's introduce this, or let's present this barrier category theorem. It says that for any complete metric space, it must be of the second category. Okay, let's see why this is true. Let's prove this by contradiction. If not, then the metric space X we must be able to write X as a countable union of nowhere dense sets, since it will be of the first category. It's nowhere dense for any K. Okay, so now let's pick up any ball. So the ball centered at x0 with the radius x0, with the radius r0. Okay, remember that previously we proved that a set is nowhere dense if and only if for any ball there exists a ball inside this ball, such that so for any ball, if a set is nowhere dense, then for any ball there exists a ball inside, such that the closure of this ball and the set E, the closure of the set E, must overlap nowhere, or must have no overlap. Okay, so this ball, what I'm going to do here is that this is my ball. I just picked up a random ball with the center at x0 with the radius r0. And because the E1 is nowhere dense, so I know that there exists a ball inside of this B x0 r0. I call this x1, and the radius I call it r1. And without loss of generality, I just let this r1 to have a radius less than 1. Because if r1 is bigger than 1, I can just make it smaller. And in this case, we know that this ball right here has no overlap, or closure of this smaller ball right here has no overlap with the closure of E1, right? This is because the E1 is nowhere dense. So I know that there exists X a ball centered at x1 with the radius r1 that is inside here, such that the closure of this ball and E1, closure of E1 has no overlap. Okay, here without loss of generality, we assume that R1 is less than 1. Okay, so now I have the first ball. And then in this first ball, B x1 R1, I know that there will be another ball. Okay, this is because, as I said, this is because the E1 is nowhere dense. And now I know that because E2 is nowhere dense. And then I know for this B x1 R1, there will be a ball inside with the radius, with center x2 and radius r2, x1, sorry, r1. And again, without loss of generality, we assume this r2 has a radius less than 1/2, such that the closure of this ball and the closure of E2 has no overlap. But remember that this is a ball that is also inside this closed ball, and it doesn't have any overlap with the E1 closure. closure of E1. It doesn't have a closure with E2, so I know that this ball, the closure of this, does not overlap the union of E1 and E2. So it's I as from 1 to 2. Okay, this is still empty. And you can see the pattern. I'm going to continue doing so. When we have, suppose we already have the BK, and then I can get this RK with the radius less than 1 over K, such that the closure of this ball and the union of all the previous EIs is empty. Okay, so now what we have done so far is we got this sequence of balls. We started from x1, r1. I don't consider x naught, r naught anymore. Just starting from x1, r1. I know that this is the largest one, and it includes the second one, so on and so forth. And for each of them, the radius is less than 1 over K, and the intersection of this ball and all the previous EI closure of EIs is equal to empty. Okay, and from here we're going to get a contradiction. Okay, let's see where we get this contradiction. Remember that we know that for XKP, which is the center of the ball for K plus P, I know that this is inside the ball XK RK, because I see that this is a sequence of balls that one contains each other, one contains the next. Okay, everyone contains the next one. So I know that this is true for any P. So what happens is you look at the distance between xk plus p and xk, the distance is less than rk. This is less than rk, right? And you know that this is less than 1rk. So it doesn't matter what this p is, we always have that. And this means that the sequence xk is a Cauchy sequence. And now because the original metric space is complete, I know that this sequence converges. Okay, and what this tells us is that the distance between xk and x is equal to the limit of k going to infinity, the p going to infinity, of dxk xk plus p, right? Because this, as p goes to infinity, this one goes to x. That's why I have that. And since distance is a continuous function, so this, according to our derivation above, this is each of this is less than rk. So when I take the limit, it is going to be less than or equal to rk. And I know that this is less than 1 over k. Okay, but anyway, I don't really need this. I can just stop at the rk. Okay, and this implies that this xk is X, is inside the ball centered at K with the radius RK, but I have to take a closure because it's less than or equal to RK. But no matter what, as we showed before, for each of this ball, I know that this intersects with this nowhere. Okay, and here what we showed is that for each fixed K, I should say here, for each fixed K, I know that the distance is less than that, so that's why X is less than, X is in here. So X is in here for each K. And since this does not overlap with this set, and that means X is not in the union of this to K, the E I bar for any I, for any K. But remember that if it's not in this for any K, that means X is not in the union for K from 1 to infinity of E K bar. Okay, and apparently this implies that X is not in the space X. Okay, now let's see an application of the Baire category theorem. It actually gives us a very interesting result. Remember that the Weierstrass constructed a type of functions that are continuous everywhere in the interval, but it's nowhere differentiable. Okay, it's not differentiable at any point. So it's continuous at every point, but it's not differentiable at any point. So this is we thought this is very rare. It's very counterintuitive. But indeed, such a function exists. So the function, say, over the interval 0, 1, the f is continuous, but for any x inside 0, 1, the f derivative of f at point x does not exist. That means f is not differentiable at point x. So there is such kind of example, such kind of functions do exist. But from the Baire category theorem, we actually can show that this is actually the majority of the set here. Okay, and what we can do, what we can show is that this, if we equip the standard distance d, as we said, the dx y to be x and y to be 2 points in this space, then we define it to be the maximum of x t minus y t. Right? This is how we define the norm, the distance. And we show that using this distance, this set here is complete. So it's actually a complete metric space. And we're going to show that functions like that is functions that in this space that are nowhere differentiable actually form a set of second category. And this, or I should say this, we can show that the functions that are in this space, let's look at this set. I should say this here. Let's look at this set. So this is a subset of the C1. Okay. And we can show that this set here is actually of the first category. And this set here, since it's a complete metric space from the Baire category theorem, we know it is of second category. So that means the complement of this set must be of second category. Otherwise, the union of the two will be still a first category. Right? So I know that the complement of this set is of second category. But what is the complement of this set? The complement of this set means it's a collection of functions, or it's a set of functions that are nowhere differentiable. So this is how we show that actually continuous functions that are nowhere differentiable actually form a set of second category. It's actually the majority of this space. Okay, so let's see why this is true. So we're going to use the barrier category theorem to show this. Okay. Okay, so we said that this E is a set of functions that are nowhere differentiable. So the E complement, we're going to show that the E complement is of first category, okay, as we planned. Okay, how to show this? To show that the E complement is of first category, we need to show that the E complement can be written as a union of a countable union of nowhere dense sets. Right? So first of all, let's look at what's the EC. EC is actually the set here. The E complement is actually the set here. Means that the functions in E complement is differentiable at least 1 point in the interval 0, 1. Okay? So the E complement is the function. It's the set of continuous functions that are differentiable at least 1 point. Okay, then how I'm going to show this is the countable union of nowhere dense sets? I'm going to introduce a sequence of sets like this. So the AK for each natural number k, I'm going to define the AK to be the set like this. Okay, so this is the definition for my AK. So let's take a closer look of this. So it's a set of functions f such that there exists some point s on the interval 0, 1, at least as long as there is 1 point s, such that this inequality holds for all the h that satisfies this. Okay, I will say that if a function is continuous at a point s, then the function f must be inside this AK set. The reason is, if the limit exists, that means, let's look at what this one is. This is supposed to be the limit as h goes to 0, have f of s plus h minus f of s divided by the h. Okay, so if this exists, then this should also exist. If I take the absolute value, it doesn't matter. This should exist as well. So if this exists, that means for h small enough, this should be less than or equal to some m, or I would say less than or equal to some k. Okay, k is some integer. So if it's differentiable at the point s, then this should be less than or equal to some k. And then I can choose this s. Since s is approaching to 0, then I can say that when the h is inside the 0, it's between 0 and some delta. But that delta, I can put it as 1 over k. So as long as my h is like this, this is small, that'll be fine. So if this 1 over k is still too large, I can continue decrease this k, but increase this k. So in this case, this will get smaller, but this will get larger. So it is more relaxed. So you have more chance to have a derivative or for this limit to be under this k. Okay, so if you increase k, this will be even relaxed. But if it's differentiable, that means this must be less than or equal to some number k. And in this case, you know that if f is differentiable at some point, it must be inside 1 over this a case. Okay, so my argument is that if f is in EC, then df is in a k for some k large enough. Okay, and what this tells us is that this EC is inside the union of this a case. Okay, now to show that the complement is of first category, I just need to show that this AK, all these AKs are nowhere dense. Okay, so that's my plan. So we need to show that AK is nowhere dense. Okay, so to show that each AK is nowhere dense, I'm going to do this in 2 steps. Remember that a set is nowhere dense means that I need to show that the interior of the closure of each set is empty. So the first thing I'm going to show is that the AK is closed. And in this case, you know that the AK complement is just equal to AK itself. Okay, so this converts to, or this is equivalent to just showing that this is equal to empty. So that's the one thing. The second thing is I just need to show that interior of AK is empty. Okay? And with these two, I can show that this is true. Okay, so now let's first show that the AK is closed. So to show that AK is closed, I just need to show that the AK complement is open. I'm going to claim that the AK complement is open. Well, how to show this is open? I need to show that for every point is an interior point. Okay, to show that, let's say that for any f in the AK complement. So you see in AK complement, what does this mean? AK is this. Okay, is this. So if it's in AK complement, that means, let me write it here. The AK complement will be the functions. This is our universe, so that's the whole set. For any s in 0, 1, there exists some h. Apparently, this h depends on s. So I'm going to write it as hs, that is between 0 and 1 over k, such that this does not hold. This does not hold means that this is actually greater than k. Okay, so such that f of s plus hs minus f of s divided by hs is greater than k. This is my AK complement. Okay, so that means if f is in AK complement, then f should satisfy that. Okay, should satisfy that. So as I just copy what I just wrote, for any s, there exists hs between 0 and 1 over k. So this is closed or open doesn't really matter, right? And also, if the s is really close to 0, I just need to consider the hs such that s plus hs is still less than 1. Okay, so I don't really need to be as far as 1 over k, because everything will be just within or just between 0 and 1. Okay, so for any s, I know that there exists this such that the f of s plus hs minus f of s, this should be bigger than hsk, just multiply the hs to the right. Okay, can move hs to the right. So it must be bigger than that. Okay, so in this case, I'm going to define epsilon s to be a very tiny number. So now, remember that this is hs times k. This is f of s plus hs minus f of s. Okay, so there's some distance between them. So my epsilon s will be just a quarter of the distance. So it'll be just a quarter of f of s plus hs minus f of s minus hs k. Okay. So I know that this must be positive. And what am I going to do with this epsilon s? Well, for this epsilon s, I'm going to look at, remember this is the s. This is s plus hs. Okay, so I know the function f is continuous. So that means it must be continuous at every point. In particular, it will be continuous at the point s and the point s plus hs. Okay, so for s, there is a neighborhood such that the function values of the points in this interval will be not far from the function value at s. And I'm saying not far from, meaning that the distance is less than epsilon s. So I call this js. Okay, so the js is defined in the way that for any sigma in js, the distance between f of s and f of sigma is less than epsilon s. Okay, so apparently I can do the same thing for this neighborhood. And this neighborhood may have a larger or smaller interval, but I'm going to choose the smaller one between the two, so that the js is chosen such that for any point in the js, this holds, and also for any point in this js plus h, which is the s plus hs minus f of sigma plus hs. The distance of this is also less than epsilon s. Also less than epsilon s. I'm just choosing the smaller radius such that both of these two hold. Okay, because the function f is continuous at these 2 points. So this is how I'm going to choose the js. So there exists a js, which is the open, I would say, open neighborhood of s. Neighborhood of s such that f of s minus f of sigma is less than epsilon s, and f of s plus hs minus f of sigma plus hs is less than epsilon s. Okay, so let's see what that is. This is s, and I'll have some sigma here. And this is s plus hs. And here I'm going to have the same, just shifting it by hs. I'm going to have h sigma plus hs. So what I can show is that there exists some js that is small enough so that for any sigma in JS, these two holds. These two hold. Okay. So with this, what we can do is we'll look at the f of s plus hs minus f of s. Okay, by triangle inequality, I can show that this is less than or equal to f of s plus hs minus f of sigma plus hs. And then plus, I'm going to erase this since I already wrote it on the left. This is going to be less than or equal to this plus f of sigma plus hs minus f of sigma. Then plus f of sigma minus f of s. Okay, I will have this. So on the one hand, I know that this is going to be less than epsilon s, as we showed here, right? This two shows that this is less than, no, I should say, this two inequalities shows that this is less than epsilon s, and this is less than epsilon s. Okay, so the right-hand side is less than this plus 2 times epsilon s. That's what happens on the left-hand side. That's what happens on the right-hand side. And then look at the left-hand side. Left-hand side, this is going to be greater than hs. Okay, I know that's greater than hs. Actually, it is equal to, as we define this is going to be just hs times k plus 4 times epsilon s. So this side is hk, so hs times k plus 4 epsilon s. Okay, so the left-hand side is equal to that. The right-hand side is less than equal to, or is less than this plus 2 times epsilon s. So I move the 2 epsilon s to the left. I will be able to show that hs times k plus 2 epsilon s is going to be less than f of sigma plus hs minus f of sigma. Okay, so that means for any sigma inside this interval here, the distance between these two is bigger than this. Okay, now this is what we can show for each point s. I will have this. Now consider the whole interval 0, 1. Then apparently the 0, 1 is covered by the union of this JS, where S is in 0, 1, or 0, 1. Okay. Actually, I can also do this. Probably I can also do this for, let's say, just to put it as closed. Doesn't matter. So everything is closed. Okay, it doesn't matter. And here I'm going to show S is inside 0, 1. Okay, so since 0, 1 is covered by these open sets, and the 0, 1 interval is a compact set, so this means that there exists a finite subcover for the 0, 1 interval. So there exists S1 through say Sm, such that the 0, 1 is just covered by the finite many of these open intervals. Okay, I would be able to know that. And so now there are only finite many of these SIs. So for each of these, I have those epsilon SI, HSI, right, JSI. Okay, so let's take set epsilon to be the smallest one of them, to be the minimum of epsilon S1, epsilon S2, all the way to epsilon Sm. Okay, so this apparently is a positive number since it's a minimum of a set of a finite number of positive numbers. So the epsilon is greater than 0. Now, for any g, and this g function is in the ball centered at the original function f here. So it's that this is a this is the f for any f. I know that there exists such a epsilon, so that for any g inside this ball, meaning that f minus g is less than epsilon. We know what? We know that for any I from 1 to m and any JSI, I will have G of sigma plus HS minus G of sigma. This should be less than, or I should say, I should say that this is greater than or equal to f of sigma plus HS minus f of sigma minus f of sigma plus HS. I should say MSI minus. So the idea is, again, just use the triangle inequality. So, but I'm moving two elements on the left to the right. So that two elements should be f of sigma plus HSI minus f of G of sigma. Let me still write it. Maybe it's better in this way. So I know that f of sigma plus HSI minus f of sigma. This is going to be less than or equal to f of sigma plus HSI minus G of sigma plus HSI plus G of sigma plus HSI minus G of sigma plus G of sigma minus f of sigma. So this is the triangle inequality. And again, here, I know that this is going to be less than epsilon because that's the distance between f and g. The maximum distance will be less than epsilon. So this is less than epsilon point-wise. So this is also less than epsilon point-wise. Okay, and altogether, I'm showing that this g of sigma plus HSI minus g of sigma. This is what at the second term on the right. This is going to be bigger than or equal to, actually it's bigger than, the f of sigma plus HSI minus f of sigma minus 2 epsilon. Right? I move the 2 epsilon to the other side. That's how I get this. So when I have this, on the one hand, I know that this here is bigger than, remember what do we have? It is bigger than this. For, we have this one. For each SI, I just need to put I here. Okay? I just need to put I there. And here this is going to be greater than K times HSI plus 2 epsilon. But there's another 2 epsilon subtracted, so this is just bigger than K times HSI. Okay, and from here we can see that this G is also inside the AK set. Okay, because this is true for any sigma. Sigma is any number on the interval 0, 1. Right? Any number in the 0 to 1. Since this already covers the 0, 1, all these things cover 0, 1. So if sigma is from there, if sigma is in between 0 and 1, then sigma must be inside one of them. And as long as it's inside one of them, we'll get this. So this implies that G is also inside AK complement. And since G is arbitrary in this ball, so that means the entire ball here is inside here. Okay? The entire open ball is inside the AK complement. And this implies that the AK complement is open. And it's open means that AK itself is closed. Okay, so that's the first point we proved. We show that the AK complement is open. Now let's try to show that the second one. So we know that from that I know the AK itself is closed. And this also means that the AK is equal to the AK complement, right? So the second item is to show that the interior of AK is empty. Okay, now we need to show that the interior of AK is empty. Okay, remember how do we show that? To show this interior point with AK is empty, then we need to show that there's no interior point of AK. There's no interior point of AK means that for any point, I call it F, and for any neighborhood of this F with the radius epsilon, there exists some point in here that is not in AK. Okay, so that means F cannot be an interior point. So I need to show this for every F. I need to show that every F in AK is not an interior point. And to show that, I need to show that for any epsilon, there exists some point in here such that it is not in AK. Okay? So this is my plan. So for any F in AK and any epsilon, I know that there exists, so let me remove this. I know there exists some polynomial P such that the distance between this P and F is less than half epsilon. Right? This is because the polynomials are dense inside the set C01. Okay, so that means for every continuous function, I know that I can be arbitrarily close, approximated arbitrarily close using a polynomial. So this is how close it is. So now, since this P is differentiable, right? It's a polynomial, so it's actually smooth. It's actually in C01, infinity, C infinity 01. And I don't really need that. I just need the P to be differentiable. We know that the P prime is also continuous on 01, and that means there exists some number because it's continuous. P prime is continuous. We know there exists. It can reach to the maximum over this interval. So there exists some m such that the P prime of x is less than or equal to m for every x in the interval 0, 1. Okay, that's something we know. Okay, so that's one thing. The other thing is because the derivative is less than or equal to m, I know that for any s in 0, 1 and any h in 0, 1 over k, I know that the p of s plus h minus the p of s, this is going to be equal to the p prime at some point between s and s plus h. So let's say it's c times s plus h minus s, which is just the h. But this thing is going to be less than or equal to m. So that's why this is less than or equal to m times h. Okay. So I know this. But on the other hand, I can get a function g which is continuous. Which is continuous, and it is piecewise linear. And the slope, so the magnitude of g is really small, it's less than half epsilon. But on each interval where the function is linear, I wanted the slope to be larger than m plus k. Okay, so that g to be this such that the magnitude of g is really small, it's less than half epsilon, and the slope of g on each, this g is piecewise linear or piecewise affine. So that means over the interval 0, 1, the magnitude is really small. So this is a half epsilon, this is negative half epsilon. So I know my g is in between, but at the same time, I want it to be piecewise linear, and the slope is really high. So it's like this, really, really high slope, large slope. Okay, and the slope is going to be bigger than or equal to m plus h, m plus k, sorry. Okay, so this m is the magnitude of p prime, as in here. And this k is for this particular k. Okay, I know such g exists. So what we can say about this p plus g? So the p is really close to f, and it's also smooth. But I'm going to add p and this g, which is also really fast. So what I'm going to get is the p plus g minus f. According to the triangle inequality, this is less than or equal to p minus f plus the norm of g. I know that both of them are less than half epsilon. The first one is because p is approximation of f, as we said here. The second one is that the g itself has a bounded magnitude. That's why I have this, and that means this is equal to epsilon. Okay, so what this tells us is, as I showed earlier, if this is f, and this radius is epsilon, I want to show some point in f. So for any f and for any epsilon, I want to show that there exists some point, and this point is going to be my p plus g, such that this p plus g is not inside ak. Okay, that's my plan. Okay, so how do I show? I already showed that p plus g is inside this ball. Now how do we show that it's not in ak? So to show that, let's look at this distance. The p of s plus h plus g of s plus h. Since I'm treating the p plus g as a function, I need to put them together. So this minus g ps plus gs. Okay. So according to the triangle inequality, this is going to be greater than or equal to the g of s plus h minus gs minus p of s plus h minus ps. Okay, so on the one hand, so this is by triangle inequality, easy to show that. So on the one hand, I know that this is bigger than, as we showed before, the g oscillating really fast, the slope is always bigger than this m plus k. Okay, so that's one. Another thing is this, as we showed before, this is going to be less than or equal to m plus h. M times h. Okay, so on the one hand, the slope is bigger than that. That means this is bigger than this times h, but this one is smaller than m times h. So altogether, this is still bigger than k times h. Okay, so it's bigger than k plus a k times h, means that the function g, so that means the function p plus g is inside the ball centered at f with the radius epsilon, but the p plus g is not inside AK. Okay, and this means that, so this point p plus g is not inside AK. Hence, the AK, since the f is not an interior point of AK, and we said this f is arbitrary, so that AK does not have any interior point. Okay, so with this, we show that the AK is of first category. Sorry, the AK is nowhere dense, and since the E complement is the union of this nowhere dense sets, we say the E complement is of first category, and that means E itself is of second category. So that is the E, which is the set of functions that are nowhere differentiable. Okay, so now let's quickly get a quick review of what we have proved here. So we want to show that the set of nowhere differentiable continuous functions, which is this E, is of second category. And to show this, we just need to show that the E complement is of the first category, because the set here is complete metric space, so it must be of second category. To show that, we first write down what is E complement. We said it's a set of functions that are continuous at least 1 point between 0 and 1. Okay, and then we define the AK to be this. Okay, and then we want to show that the E complement. We show that the E complement is actually the union of the AK case. So if I want to show this of first order, first category, I just need to show that each of this AK is nowhere dense. Okay, and to show that, we need to show this is true. And to show this, we will show that AK itself is closed for every k, so that I can remove this bar here. And secondly, I want to show that the interior of each AK is empty. So to show that each AK is closed, I just need to show that the AK complement is open. And to that end, I show that for each point f, there exists a epsilon small enough. There exists a epsilon small enough so that every point in the neighborhood is in the AK complement. Okay, so that's what we did here. So we found this epsilon such that for any g in the neighborhood of f with the radius epsilon, the g is also inside the AK complement. That's how we show that this is actually open ball that is inside the AK complement. That shows that the AK complement is open, and then AK is closed. Okay, so that's the first one. The second one is that we want to show the interior of the AK is empty. And to show that, we just need to show that for any point f in AK and any epsilon, we can show there exists some point inside this ball that is not inside the AK. And this shows that f is not an interior point. And because any point is not an interior point, so that means the interior point of AK, the set of interior points of AK is empty. Okay, so to show that, the key is to get this f, p plus g. And this p is a close approximation of f, since the distance is less than that. And then we know that p is differentiable, so the p prime is bounded by some m. Okay, and we get a smooth approximation of f, but we're also going to get some non-smooth function, non-differentiable function added to p, so that the p plus this function, which we call g here, is still close to the f. So the g has a magnitude less than epsilon over 2, but the g is so non-differentiable or non-smooth, so that the p plus g is still close to f, meaning that p plus g is in here. But how non-smooth of g is? We assume the g to be a piecewise linear function. I want the g to be like this. But the key is that if we want to show that p plus g is inside ak, I want to show this. Right? I want to show that this is bigger than this for some, for any s, I want to show that this is bigger than this for some h. Okay? So here, the g is said to be the piecewise linear functions that has a slope bigger than m plus k. But I should say that the slope is bigger than k. So I would say each segment has a length less than 1 over k. So the reason is I want each of this, so if I zoom in, I want each of this segment here to have a length of less than 1 over k. So if I have that, then I know that for each s, it must be, no matter where it is, I know that I can find this h that is smaller than 1 over k, because say if this is where the s is, then my h will be not too far from s, and the distance between the two is inside, is still falling into the same linear segment. So for any s, I know there exists h, and this h must be less than 1 over k, as I said. We show that for any s, there exists some h less than 1 over k, such that this is greater than k times h. Okay, and this means that the p plus g is not inside ak, because ak is such that there exists some s such that this is less than or equal to k for any h between 0 and 1 over k. And now what you showed is that there exists for any s, which is actually in this case, for any s, you found some h, so that the h is less than 0 to 1 over k. And this is just making sure that, say for example, this is how you, if I zoom in, if this is where your s is, then you just choose your h to be somewhere nearby, so the s plus h. But as I said, this h is less than 1 over k, so that means you know that there exists some h less than 1 over k, such that the 2 points falling into the same portion. So you can consider the function value is equal to the difference of the function value at these 2 points is equal to the slope times the distance between the two, which is h. So that's why here we have the distance of these two is bigger than or equal to this 2, which is due to the triangle inequality. But for here, since this g is this zigzag function, so that's why the slope is bigger than that. As we said, the slope must be bigger than this, and times this distance between the 2 points, which is s. That's why I have this one. And this minus this, which is smaller than or equal to mh, due to the smoothness of p, we have this greater than kh. So for every s, we found some h between 0 and 1 over k, such that the distance of this is greater than k times h. And that means this P plus G function is actually in AK complement, or B plus G is not in AK. But at the same time, P plus G is some point near the F. So we show that this F is not an interior point. Okay, and that means the set of interior points of AK is empty. Okay, so that is, we didn't use any construction of continuous but nowhere differentiable functions. But by using the Bayer category theorem, we show that actually the set C01 is dominated by such nowhere differentiable functions, right? Since this E actually is of second category, and the E complement is just of the first category. Okay. Okay, now let's consider another question related to Banach spaces. So recall that we have, suppose we have two Banach spaces, and we have a bounded linear mapping from X to Y. Okay, so let's say that if this T is bijective, meaning that T is a one-to-one correspondence between X and Y. And the question is, in this case, I will have the T inverse. And T inverse is pretty easy to show that T inverse is also linear, right? Because T is linear. So this implies that T inverse exists. And it's also linear from Y to X. But the question is, do we have this? Okay. We know this is linear, but we don't know if it's bounded or not. Okay. So we want to answer this question. Actually, the answer to this is yes. We want to know why. And this is actually a special case, or it can be easily obtained by applying the so-called open mapping theorem. Okay. So let's discuss this open mapping theorem. And from there, we get the answer for this question. Okay, it's called open mapping theorem. Okay, the setting is this. Suppose we have X and Y, which are Banach spaces. And we have this T that is a bounded linear mapping between from X to Y. Okay, we don't really need this T to be bijective. We just need to be surjective. Then we can show this T is open mapping. What do we mean by surjective? It means that Tx is equal to Y. Right, Tx actually fill up all the entire Y. Then the T is an open mapping. So the open mapping means that it maps every open set to an open set. That means for any set that is open in X, then the TW is open in Y. Okay, I should say W is open in X implies the TW is open in Y. And in this case, we say the T is open mapping. Okay, so from here we say that if X and Y are Banach spaces and T is a bounded linear mapping from X to Y, then as long as T is surjective, then we know that T is open mapping. Okay, this is what we're going to prove. And from there, I'm going to answer the question earlier. Okay. So how do we prove this? I'm going to, since we're going to talk about the open sets, a key notation is that we need to use balls, right? Open balls. So let's say that when we write B, X, R, this is the open ball we say this is the open ball in the space X. It's open ball in the space X. Okay, when I write U, something Y, like a Y, and something R, then means that this is the ball inside the space Y that has center, that has a center Y here and the radius R. Okay, so the B denotes the open balls in X, the U denotes the open ball in Y. This is my notation that I'm going to use below. Okay, so I'm going to do this in 3 steps. So the first step is I want to show that the T is open mapping if and only if there exists some delta such that, I'm going to show that the T is open mapping if and only if there exists some delta such that U0 delta is inside the T of B01. Okay, the B01, as I said, is a ball in the space X, unit ball in the space X. T of that, it will be some set in the space Y. I'm going to show that U0 delta is inside this. So in other words, I want to show, because apparently the 0 is inside the image, right? Because the 0 is inside here. So T applied to 0 will be 0 since T is linear. So 0 must be inside this. But if you know there exists some delta such that this is in here, that means this set here contains 0 as an interior point, right? So this means that 0 is an interior point of T of B01, the image of B01. Okay, so this is the first claim I'm going to make. Okay, let's see how to show this.